Okay, I got the tables up here. All right, so I've repeated this for our benefit here. Here's the posterior predictive probability, if we want to give it a name. Here's the probability this hypothesis is true. Remember that was 1 over 52. Given equal probabilities, and seeing 4, x equal 4, was 5, 32, and 62 for each of these hypotheses. Under a different regime, under a different set of evidence that I might have come to it with, skeptical regime, I have a 69, 23, and 4. Okay, no problem. And I want to remind us the probability of getting 4 hits, assuming the first hypothesis is about 1.5%, about 9%, and about 17% under this hypothesis. No problem there. Now, all right, that's a reminder of what we just had, and I want to keep that. Now, let's imagine we're going to do the experiment. We did that experiment one time, but we could easily do it 10 times. We could easily do it 100 times, 1,000, even 10,000 is not that many. 10,000 is probably even bigger than that, maybe even 1,000,000 or more. Because don't forget, if I'm going to do lots of experiments with you, we're going to do many more than just one experiment. And that's just with you. And if I'm setting up a lab to do this, I might do hundreds with you. And hundreds with other people, and that's just at my little lab doing this stuff, and this stuff is going on all over the world, so that we could easily reach into the thousands, 10,000s, a million type of experiments, right? So let's suppose we ran the same experiment 10 times, 100 times, 1,000, 10,000 times, and I want to know, out of those experiments, given each of these hypotheses, what's the probability that at least one of those experiments, all right, we already did the probability of one experiment, but I want to know the probability if I'm going to run the experiment 10 times. What's the probability that at least one of those experiments will report a 4, all right, or greater? I can calculate something like that, right? That's kind of like calculating the probability of data we didn't see. But in this case, it's not, because I want to know what I might expect. If this hypothesis is true, what's going on in the world? How many hits when I see? I know that anything greater than 4 or greater is going to give me statistically significant results and so forth. So the point of it is, there's a 14% chance that if I run 10 experiments, there's a 14% chance that at least one of these will be statistically significant. That'll give me a 4 or higher. If I run 100 experiments, there's a 77% chance. No psychic abilities. Remember, this is our no psychic abilities, does not have the ability hypothesis. There's still a 77% chance if I run the experiment 100 times. And 100 times is nothing, order of magnitude nothing, if I'm going to be doing this a lot of times with you or with other people. This applies to either within an individual or across individuals. I mean, there's all sorts of ways we could make that even more complex, but I'll let it pass. And it's virtually certain, if we're going to run 10,000 experiments, that I'm going to get at least one of those with a 4 or greater. Now, if this is true, if the psychic hypothesis is true to the power of 2 over 52, we rapidly reach the probability we're going to see experiments that look like they're demonstrating psychic abilities, right? And here's 85% chance. If psi 3 is true, there's an 85% chance in just 10 experiments that I'm going to see one with greater than a 4 or greater, all right? And so on. That is what I can calculate if I want to calculate what I might see out in the world. That's absolutely fine. I could do something like this. But that tells us right away, though, that if I'm running the experiment a lot of times, and we're going to take 100 just as our example here, and this is how I might also do drug company results or any kind of results. I could use something like this. How many times have I already rerun this experiment, or how many experiments have I actually done, and all this kind of a thing. In real experiments and so forth, what we can do, and I'll show you in a second here, without getting into the math of it, I could take the exact data. I don't have to just take these kind of summaries. I could take the exact data, and we could do the calculations, as you'll see. But I want to take into account that I got a 4. You and I got a 4 on one of the hits, and on the other ones we did 100. Just for the sake of supposing, we did 100 Did you get it? We did 100 of these experiments. Some of them you had no hits. Some of them you had 1 hit. Some of them you had 2. Some of them you had 3. But just one did you have a 4. And none of them did you have a 5 or a 6 or anything up to 52. Now, as I say, I could take the exact results that we have and I could use those just as easily. But I don't have those exact results. I'm going to calculate something else for you. Now, what I want to know is, I want still the probability the hypothesis is true, given I got 1, 4. Given I got 1, 4, and however, I forgot to write M in all these. I want to write it, well, that'll be, I'll call it EM. EM here. Where this is going to be our M equals 100 here. But I'm just doing M experiments. I still want to calculate, I still can calculate the probability it's true that you have the ability, any of these hypotheses, Y1, Y2, or Y3, given we had 1, 4, and however many experiments, here 100 experiments, whatever other evidence we have. And that's just Bayes' formula again. I want the probability of 1, 4, given the hypothesis is true, times our initial probabilities of these these are true based on whatever evidence we're bringing to the problem. That's just Bayes' theorem again. So let's do that. And I have 2 regimes here, and I'm going to give you this is the 1/3, 1/3, 1/3, the initially completely open-minded, if you like. They don't know anything about psychic powers or the new drug or anything, so they're willing to accept this. The other person is a true believer. Not quite. They really want to believe. They really think it's true, and they're bringing something to this, okay? So they're going to think, aha. I really think that the person, not only is psychic power true, but a lot of people have a lot of it. So I'm going to give most of the weight to this. That's probably the most, dogmatic. That's not dogmatic. It's the most, the strongest one towards psychic powers. Now, what do I mean by 1, 4? This is where you can often go wrong. This is where calculations often go wrong. So you get 1, 4 in an experiment of 100 experiments. Now, what's the ways you can get 1, 4? We need to be very careful here. Well, I can do the first experiment I did could have had 0 hits. The second, and then the second experiment could have been 0. The third experiment could have been 0. The fourth experiment, I got to have 99 experiments where I had no hits whatsoever, and then I had a 4. Or the first one might have been a 4, and the other 99 were all zeros. Or the second one was a 4 with all the other zeros. Or I could have all zeros up until the very second to the last experiment. That could have been a 1, a hit of a 1, and then a 4. Or I could have had, all the other ones could have been ones, and the last one was a 4. You can see there's lots of combinations. Lots of ways to get experiments out of 100 experiments in which only one of these gives us a 4, because that's what we saw. Now, like I say, if I had the actual data, I could use that actual data. But I'm going to assume this is the only thing I have. I have the summary of the data here, because I don't have the exact number of zeros I got, the exact number of 1 hits, exact number of 2 hits, exact number of 3 hits. We're assuming we have just a summary here. So, but that is that particular calculation. We deduced something like this before. This is the multinomial. We use a cumulative multinomial distribution to get these probabilities. And so we can calculate the probability under this hypothesis psi1 of we get just a 1, 4. There's a 41% chance. Out of 100 experiments, there's a 41% chance that one of them, only one of them will have a 4. None of them will have a 5 or a 6 or higher. And the others will have any number of 0, 1, 2, or 3s. Okay, reasonable, pretty big chance. Under psi2, we only saw 1, 4 now. There is a 4 in a million, roughly, chance. Only a 4 in a million chance. That is to say, we're assuming now, we're believing that people have psychic powers to the strength of 2 over 52. And we only saw 1, 4? That's very odd. So there's only a small chance of that. We should be seeing bigger numbers, right? We should be seeing a lot more like 5s and 6s and so forth. And it's even smaller for if we assume the psi 3 is true. Psi 3 is true with the probability of getting only 1, 4. It's 10 to the minus 18th, roughly. Very unlikely to happen if psychic powers are true. However, we did this 100 experiments, and this is very similar to the way experiments run in parapsychology, and I got one that was a hit. I got one that was a statistically significant hit, and I'm going to report on that. Now I can calculate this. I can calculate the probability that each of these hypotheses are true. And it turns out, even if I start out to be very open-minded, or I'm really, really wanting to believe psychic powers are true, the probability that you have no psychic powers is near 100%. And these others are down in the mud. They're approximately 10 to the minus 6, 10 to the minus 6, 10 to the minus 16, 10 to the minus 16. There's an 8 and a 9. I got them backwards. And the reason for it is because I did 100 experiments. I only got one that had a 4 in it. And I should have been seeing a lot more if you genuinely had psychic powers. So this is another way to report this kind of a thing. I only did one experiment, and I say, if I just did the one experiment, I only report the one that I got, and I say this one's statistically significant. If I just do this experiment, and therefore my p-value is less than the magic number, therefore my hypothesis is true. The person has psychic powers. If I did that, you know, it's cheating. It's cheating. That's why we see so many results that don't hold up to scrutiny. They don't reproduce, all this kind of thing, because hypothesis testing is the absolute weakest way to defend something. This is much harder. Here, I have to have a lot more evidence if I'm doing multiple testing that I can calculate the probability this hypothesis is true. Now, I can calculate, it doesn't have to be just 1, 4. It could be whatever I absolutely got. You know, when I got however many zeros, however many ones, however many twos, threes, fours, whatever. That's what I saw. I can calculate that using the same kind of multinomial kind of a thing. But I'm assuming I only got one. So whatever we did get, we can calculate. We can calculate these same things here. Now, which one do you display? Which one do you show? Well, that's the hard part about this. This is the really difficult part about showing the probability of the hypothesis given the evidence that you have. Because you have all these scenarios to consider. You have all these hypotheses, alternate hypotheses, or ways of expressing what your hypothesis really means that you really seriously have to consider. And you have to consider multiple testing. You have to consider the exact evidence that you got. Not probabilities of data you didn't see. That's absurd. That's just nuts. We don't care about those probabilities. We care about the probabilities of what we did see and the hypothesis, whether it's true given what we've seen. That's what we really want with hypothesis testing. So, you know, and there's lots more we could have done with this. So I barely scratched the surface of this thing. We did the lady tasting tea, and that took 2 episodes just to flesh out the thing without doing any math. Here we did a lot of math. Or I hid the math, but the equations are quite simple. Except the multinomial stuff, that's a little difficult because you have to keep track of what you're summing up and everything, but people have code for this. This is why, in these 4 long, boring episodes, people don't use the correct way of doing things. It's incredibly difficult. It's very difficult. It takes a lot of work. You have to carefully plan exactly how you're going to show these things, think about them, and there'll be people invariably who, it makes it much easier for them to dispute your results. When you say the p-value is it's less than the magic number, you say, well, my hypothesis is therefore true. And nobody can really contradict you. They can bring up other evidence and so forth and kind of criticize you, but they can't do it numerically like this. This is why if you put things in this form, and give them ways to plug their own numbers in for their own prior beliefs and so forth, it's a much better way to communicate things, even though it's a lot harder, because it's more honest. And it'll lead to a lot less angst and a lot fewer false positives. A lot fewer claims will be made in science this way, but a lot better claims will be made. There'll be fewer, but the ones that we do get will be superior. All right, I mean, we still have a lot more to say on hypothesis testing. I'm going to go over p-values, and we'll do that, and that's going to be too much. But we need to do all of this. We need to do all of this, all right? So I really thank you for sticking with me. I know this is a lot of work, a lot to take in. I feel like I'm talking a mile a minute. I probably am. And we're barely covering this stuff. So there's a lot more at wmbriggs.com and wmbriggs.substack.com. Thanks very much for watching.